Hello, everyone, and welcome to today's Optica Technical Group webinar, Subwavelength Antenna Structures for Strong-Field THz Experiments in Condensed-Matter Systems. My name is Hannah Walter-Palin. I'll be helping to moderate this webinar on behalf of Optica. We're very excited to have Christoph Lange from the Technical University of Dortmund joining us for this webinar, which has been organized for you by our Photonic Materials Technical Group. So while we wait for all of our attendees to join us here in Zoom, I did want to take a moment and tell you a bit about Optica's technical groups. Optica's technical groups aim to create vibrant and active communities for all of our members to participate in. We offer members more than 40 different technical groups to choose from, and each of these groups are led by Optica members who volunteer their time to organize events that are tailored to your interests, such as today's webinar. In fact, the technical groups have been hosting webinars regularly since 2013, all of which are available for you to view on demand on our website. So you can learn more about the technical groups, find out about our upcoming events, and also access our library of over 200 on-demand webinars by visiting us at optica.org/technical groups. Now, before we start with our presentation, I want to note that we will be taking your questions at the end of the talk today. But we encourage you to submit questions for our presenter throughout the webinar, and you can do so by clicking on the Q&A button at the bottom of your Zoom window. You'll then be able to enter your questions in the pop-up box, and you're also going to see questions from your fellow attendees in the Q&A box. So if there's a question you really want to see answered during the question and answer session, hit the thumbs up button beneath it to let our moderator know. Now, finally, we are recording this webinar, and a link to the recording will be emailed to you directly within 48 hours of the broadcast. And when you disconnect today, you'll be prompted to complete a short survey and provide us with your feedback. So if you could take a moment to do that, we would greatly appreciate it. So now I'm going to turn the floor over to Christina from our Photonic Materials Technical Group. She's going to tell you a bit more about the group and introduce you to our presenter. So Christina, the floor is all yours.
Thank you so much, Hannah, for the introduction. And I'm going to go ahead and share my slides for today. I hope you can see my slides.
We can.
Yeah, so hi, everyone, and welcome to today's webinar. Also from my side, I'm really excited to have today with us Christoph Lange from the Technical University of Dortmund, who will show us how metasurfaces, metamaterials, and also antenna structures can be a gateway to condensed matter experiments. And with a specific tilt, he will show us how terahertz fields can provide quite unique insight into these systems. But before we go ahead with our speakers, let me first introduce to you the group who, as Hannah said, dedicates their time and energy to organizing events such as the one of today for you. So we are a group of 5 early career scientists, among which Sander Mann, who is our event officer, Georgia Papadakis, she's also one of our event officers. She's currently at ICFO, Maxim Sherbakov at UC Irvine, and Dimitrios Tsaroukis, who is our chair, who is also today with us. And I'm Christina, and I'm really happy to host today's event for you. First, let me also introduce a little bit more in details the Photonic Metamaterials Technical Group. So our group provides a forum for those who work on problems with on fundamental and applied aspects of waves in random and periodically nanostructured materials. And we connect our members, which by now are more than 2,000, through our community, through technical events, webinars such as the one of today, networking events, and hopefully soon also more in-person events. And as of 2021, we also introduced some new formats for you, among which I would like to mention 2. So keep an eye on them as they will appear more in the future, hopefully, which we call dialogues. One being dialogues on metamaterials, past, present, and future, which happened at CLIO last year or this year. And the second one, dialogues on imaging with metasurfaces, challenging and opportunities. So if you want to stay up to date with our events, please feel free to join our online community through the different channels. We have a website at the Optica website. We have a group on LinkedIn. You can follow us on Twitter. Feel free to follow any of the members of the technical group on Twitter to be informed about these activities. And also you can email us at this email address. I will make sure to post all of this in the chat after we introduce today's speakers, which is actually the most exciting part. So I'm really, really excited to introduce to you Professor Christoph Lange, who is currently a full professor at the Technical University of Dortmund in Germany. And Professor Lange's research concentrates on investigating quantum phenomena in solid-state materials that happen on very short time scales, on picoseconds down to femtoseconds. And today we will see also how Professor Lange's team makes use of subwavelength resonators that may be switchable to control and boost interactions between light and matter. And we will learn today how important metamaterials and nanoscale resonance engineering is for this kind of studies. So with that, it is my greatest pleasure to give the floor to Professor Lange and listen to his talk.
Thank you very much, Christina, for the very kind introduction. Thanks also for having me in the first place. Thanks to you and Dimitris. And also thanks, Hannah, for taking care of the organization of this webinar. So I'm happy to round up, so to say, and to present an overview of the physics that we've explored over the past 10 years almost, I would say, that all can be summarized as strong field physics in the terahertz range occurring in custom cut, tailor cut metamaterial structures or resonator structures where the near field is shaped to achieve a certain functionality. Let me set the stage for the physics that I'd like to discuss today. I'd like to essentially recall for every one of us how light and matter interact. Often we learn textbook style that we have weak and rapidly oscillating fields which create a superposition between some initial and some final state, and this kind of light matter interaction occurring over many, many cycles of the optical field is described by the minimal substitution Hamiltonian, where we plug in the electric field of the incident wave by its vector potential, and then we expand this, we drop a square terms which lead to higher order terms in the electric field of light matter interaction, and then we can derive Fermi's golden rule, which tells us something about the transition rates between the initial and final state. The dynamics of this transition, what happens on a subcycle timescale, are more or less irrelevant here. So they are mostly hidden to us. It's a black box that where we just learn about the transition occurring itself, not about its dynamics on very short timescales. On the contrary, when we apply an extremely strong field to an electronic system, for example, this atom here, this field will create a superposition of many different quantum states, and these dynamics will now be governed by a whole range of different effects, including tunneling effects, ionization effects, or harmonics generation. Here, it's the subcycle effects that govern the dynamics and the physics that occur in this regime of light matter interaction. It's not, strictly speaking, necessary to have extremely strong fields to observe such subcycle dynamics. They can actually be observed across a large range of electric field amplitudes. At the upper end of the scale, we have certainly phenomena like harmonics generation or sideband generation, tunneling effects driven by the terahertz field. We have the possibility to use these fields for scanning, tunneling microscopy, atomic force microscopy. We can manipulate spins on very short timescales, as I will show later on with these fields. And then gradually going down this electric field amplitude scale, more subtle effects, resonant excitation of inter-subband transitions in semiconductors, for example, acceleration of electrons in Dirac materials. And finally, arguably at the low end of the scale, even vacuum fluctuations, vacuum photons can drive dynamics that occur as rapidly as the oscillation cycle of light itself. Now, we've heard in the introduction, and this is also what this technical group is about, that this is about metamaterials. But I'd like to start with a basic distinction, namely metamaterials as typically an array of resonators versus individual resonators and how their functionality in each case is used. I would say a definition of a metamaterial could be that it's a periodic structure which is patterned on a small spatial scale below the wavelength of the light that it's supposed to manipulate. And on this basis, with an entire periodic structure, you can manipulate the electromagnetic properties, that is epsilon and mu, in the far fields. And you can do this in a way that goes beyond what you can do with the constituent materials, so beyond what natural materials can do for us. Examples by no means complete, because this is an extremely wide field. So just a glimpse into this multifaceted terrain, so to say. Examples include a publication by Smith just a bit over 20 years ago, investigating the dynamics or the response of such resonator structures, an entire array of them, achieving simultaneously negative epsilon and negative mu. Then by Federico Capasso's group just a few years ago, the ability to manipulate light actually on visible wavelength scales. You see a periodic structure here where these little boxes, which are on the scale of just a few tens of nanometers, are rotated bit by bit, shaping locally the phase of the light field and then achieving in the far field focusing capabilities, just as regular lens does, but in fact with less spatial aberrations, or even three-dimensional structures, as rounded up just nicely in this recent review here in the group of Martin Wegner. On the other hand, we have individual resonators, which I would for this purpose characterize as structures where you can shape electromagnetic fields on these extremely sub-wavelength scales to achieve certain functionalities. I'll just show kind of an image to illustrate this. This is a calculation of the near field of one of the resonators we have worked with. I'll get back to this one later in the presentation. And one property of such a resonator can be the enhancement of the electric near field somewhere inside this terahertz cavity as a function of the frequency, for example, showing here enhancement factors of up to about an order of magnitude, which already hints at this possibility of increasing the strength of light-matter interaction in these structures by orders of magnitude. So the distinction between the two in the context of what I'm going to present would be that metamaterials shape the far field in certain ways and are very flexible and powerful in doing this. But the resonators I'd like to discuss today, they are just the unit cells, the individual elements of such metamaterials. And there the near field is absolutely crucial, because here we want to exploit the possibility to shape this near field and to achieve certain interactions in this near field that are otherwise not the focus when we talk about metamaterials. I'd like to give a little bit of an appetizer to this with a couple of examples that I will then go through in more detail. And one is the possibility to control spins by strong terahertz fields on very short timescales. The idea there is to use one of these antennas as a concentrator for the terahertz radiation to increase the near field amplitude, by more than a factor of 20, and to achieve very strong fields in the center of this resonator of up to 25 megavolts per centimeter, which are then sufficient to actually control spins on the timescale of their oscillation cycle. The second example is related to tunneling, interband Zener tunneling, actually in a semiconductor, gallium arsenide, where the resonator also enhances the field locally and drives this process in which up to 500 terahertz photons are upconverted to a single near-infrared photon, showing you the extreme nonlinearity that this process brings. And then the range of very low field amplitudes, the field amplitudes of quantum vacuum fluctuations, where extremely strong light-matter coupling is achieved with vacuum Rabi frequencies exceeding even the carrier frequency of light by up to 43%, which leads to a strong population of the ground state with vacuum photons of these structures. So here it's even subcycle polarization dynamics driven by the vacuum field, and I'll also get back to this later in more detail. The general approach to designing the light-matter interaction in these structures is to fully control the near fields in frequency and also in space on this subwavelength scale. The common recipe is to design a structure and to calculate its near field profile in the following way. This is an example unit cell with one of our resonators here. We then implement the electronic excitation if that is necessary beforehand by its corresponding dielectric function. This is one example here where we investigated cyclotron resonances of Landau quantized electron gases just below the meta structure here. The cyclotron resonance in this case is described by this anisotropic or gyrotropic dielectric function, which implements the physics of, well, classically speaking, electrons going in circles, or quantum mechanically speaking, the Landau quantization. We then take this volume with all the properly defined dielectric constants, and we discretize it into individual blocks, into a mesh. And then the task is obviously to solve Maxwell's equations on this mesh. So the task actually numerically boils down to investigating all the continuity conditions at adjacent cells here. So each cells that you see here, they are coarser cells here on the outside of the volume, and where the structure is finer spatially, the cell structure becomes smaller. So there are more cells there. In total, we can have hundreds of cells, up to 10,000, up to 1 million of cells, depending on how fine-grained we want to learn about the near field, calculate the near field properties. So each of these cells then has a neighbor. On each of these interfaces to the neighbors, there's a continuity condition defined by Maxwell's equations. It leads to a large matrix that defines all these continuity conditions. And this is typically today routinely solved by various Maxwell solvers, some of which are available as open source, some of which are commercial, but essentially they all do the same job. They all give us the electric field distribution in these resonators. For example, here, the near field profile along the growth direction of the particular structure you see in the top left corner. So we can discern here the exponential decay, the evanescent part of the resonator mode. Then here in the sample or in the metamaterial plane, a drop of the near field, and then we on the opposite side have the same kind of behavior. A bit more illustratively, this is a video actually of the picture that I showed before. This is an actual calculation of the near field. It shows a plane wave incident here from below through the substrate, with the polarization as indicated here by the red arrows. And this plane wave now excites resonantly this resonator structure. The resonator, you're seeing 3/4 of it, 1/4 of it is cut away here for visualization. The resonator consists of several parts. We have a central part which looks like a capacitor structure and acts just like that. Then we have this path here where electrons in the gold can be accelerated by the incident near field, giving rise to a current. And also because it represents a single turn of a coil, it has an inductance. And then, of course, since we have a dissipative material, we also have a resistance. Taking all these three together, we have an RLC circuit, an essential resonant electronic circuit just operating with, well, propagating light waves here in the terahertz range. This one here is resonant at about 0.8 terahertz, but it's also possible, obviously, to design these up to tens of terahertz if necessary. One feature you can already recognize here is the first of all, the uniform nature of the incident plane wave here from below, and then the shape of the resonator mode, which clearly deviates from this uniform structure of the plane wave, and also which concentrates the electric field very strongly here in the center, where this capacitive region of the resonator is located. So with this preface, let me now discuss the topics that I've already given you a teaser for in each case. The first one would be switching of spins in the near field of these terahertz structures. This here is actually a graphical representation, an artistic one of a Bloch sphere of a spin initially residing in one orientation, then, as we will see next, being strongly excited by the strong terahertz field and being forced to change its orientation into an adjacent local potential minimum, where it then eventually ends up. So the idea here is to switch spins between different local potential minima with the ultimate goal of a picosecond magnetic storage devices. Control of spins by light is obviously technologically highly interesting. It's the foundation of spintronics and quantum computing, also in ultra-fast data storage. And I'll just be brief and wrap up a little bit the history of the field of femtomagnetism, which didn't start in the terahertz range, certainly, but with femtosecond near-infrared pulses. One of the first investigations was by Beau Repaire and Jean-Yves Bigot's group, where a femtosecond near-infrared pulse was used to heat up the spin bath, the spin temperature of nickel, ferromagnet, on a very short time scale, and thus by destroying the ferromagnetic order, essentially it's possible to destroy the magnetism on a very short time scale, or in other words, a first approach to controlling magnetism on very short time scales. Ever since then, more sophisticated schemes came up, inducing precessional dynamics in spins, inducing spin reorientation by the laser field, exploiting an inverse Faraday effect by which a magnetic transient field is created on the sample, all the way up to non-thermal photomagnetic recording and light wave control of magnetism. Even industry has caught up. Just a few years ago, Seagate announced a heat-assisted magnetic recording, which is in a way an implementation of the findings of Beau Repaire and Bigot, by which a laser weakens the magnetic order on the hard drive before it is being written to by a conventional coil-based write head. Now, all these schemes using optical, near-infrared, or visible light have one thing in common, one common deficiency, I would say. They use photons which are located in the electron volt range, whereas spin excitations always live on the milli-electron volt scale. So these excitations are always necessarily somewhat indirect. Electronic wave function degrees of freedom are excited, or phonons are excited, and they then somehow act back on the spin system and cause a change of the magnetization. So this is inherently connected with a low quantum efficiency. Undesired degrees of freedom, thermal excitations are induced, and thus the spin deflection angles are limited, whereas applications would require a very efficient control of the spin orientation for storage or computation. There's a different approach which uses terahertz pulses. In this particular case, we don't have this discrepancy of the two photon energies. We have photon energies of the terahertz wave which live on the same scale as the spin excitation. So we bypass this indirect channel of controlling spins. One implementation uses the Zeeman torque. So in this case, it's not the electric field of the terahertz pulse, but rather the magnetic field that directly induces a torque of the spin system and leads to a deflection of the spins, in this case, on the order of 1 degree. Now I want to present a different approach, which also uses terahertz radiation, but which does not use the Z-man interaction. Z-man interaction has this one disadvantage of scaling linearly with the field, so just like the square root of the intensity. So in order to really achieve spin switching, one would have to drastically increase the incident intensity. Here, instead, I would like to propose the idea of addressing orbital wave function degrees of freedom in suitable materials, which then by spin-orbit interaction directly attack the spin degrees of freedom. And this would bring all sorts of benefits, not dumping the excess energy that near-infrared photons do, but still exerting a very direct torque on the spins. One material where this is possible is thulium orthoferrite. The crystal structure is shown here on the left-hand side. The magnetism comes from the ion spins, whereas thulium controls by the spin-orbit interaction the magnetic anisotropy potential. In this material, the ground state of the thulium ions is split into several states, and as these are excited, for example, by temperature, by just raising the temperature, the magnetic anisotropy potential changes in a way that rotates the spins by 90 degrees within a temperature window of about 10 kelvins from 80 to 90 kelvins. Temperature, of course, is slow, so we don't want to exploit temperature, but rather we want to now address these ground state split transitions directly using terahertz radiation. So the idea is to excite these states very rapidly on a very short time scale, much faster than the spin dynamics, and then to induce very strong spin oscillations by shifting the spin potential on a very short time scale. This is a first result of this experiment investigated by Sebastian Bayerl from Rupert Huber's group a couple of years ago, where he investigated bulk thulium orthoferrite by strong terahertz pulses. The first thing that happens when you excite the material is you see a resonance at about 800 gigahertz, which is in fact a so-called quasi-antiferromagnetic mode. It's also launched by Z-man interaction. But then as you increase the field amplitude, there's a dominance when you go to high fields of another mode, which is slower and is superimposed now onto this rapid oscillation. So that one emerges here at about 85 gigahertz. It's called the quasi-ferromagnetic mode. And this is the one which is launched by these transitions that we are driving between the thulium ground states by the strong terahertz field. And also the scaling of this mode, which is the one here in red, with the incident field is quadratic rather than linear. So this is also confirming its nature being dipolar electric transitions rather than the Z-man interaction. So with this favorable scaling, it should be possible now to drive very large spin oscillations that ultimately are sufficient to lead to spin switching in this material. From calculations, from a simple estimate, it's clear that we need about a 5-fold increase of the terahertz field, but we were already operating at a megawatt per centimeter, so quite a strong field. And this is, of course, as you already guess now, where we invoked the terahertz antenna to further boost the field. This is the experiment. The terahertz field excites this particular antenna structure here, and then we have a near-infrared probe that is funneled through the centerpiece of the antenna, and there by Faraday rotation, it probes the state, the magnetic state, as a function of delay time. This is a calculation again of the near field property of this antenna. So here we see the near field distribution. It's relatively homogeneous here in the center, with more than 10 megawatts per centimeter right in the center, and the lobes of the antenna up to 25 megawatts per centimeter. So that should be sufficient to actually drive terahertz induced spin switching. The antenna is a pretty open design when you compare it to the one we discussed before with the outer induction loop. That one is missing here, which makes this antenna particularly broadband to absorb as much radiation as possible from our incident terahertz pulse, and also at the same time to cover the spectral range of these thulium transitions that we want to address. So these were the two design aspects of the antenna. Now we can test the performance of this antenna in a first attempt. This is the structure without the antenna. So here we investigate the bulk material again for reference with 1 megawatt per centimeter of far field amplitude. We again see the two modes, the slowly oscillating one, which is the one we're interested in, as well as the rapidly oscillating one, which we don't directly want to address. And then moving to the antenna, and actually lowering the field by a factor of 2.5, we see a stronger oscillation, first of all, and we also see that the oscillation now is predominantly at the lower frequency. And the high frequency part is almost entirely gone. So this is good news. We have achieved the strong scaling with the antenna, and at the same time, as a byproduct, the Z-Man launched mode has completely disappeared almost. That's for two reasons. First of all, with higher field amplitudes, of course, the electric field dipolar transition mode will dominate, but at the same time, the metamaterial, our resonator, only selectively enhances the electric field and actually even suppresses the B field. So that's two ways by which we now have a preference for the desired magnetic mode. We now increase the field amplitude to higher values and do actually an entire series on this antenna structure. Low field amplitudes in the far field lead to a coherent oscillation as shown here. As soon as the system is excited here at time 0, here on the right-hand side, we have the spectrum with the magnetic quasi-ferromagnetic mode here showing up. Now increasing the field amplitude, this trend continues. The oscillation becomes stronger, but it also slightly changes character, which you can also see right here in the spectrum, which slightly changes shape. There is a critical amplitude, in this case, 0.75 megavolts per centimeter in the far field, where something fundamentally different occurs. Namely, there's now first a reduction of the transient magnetization oscillation, and there's a local minimum, that's about this one here, and then there's a slight recovery of the amplitude. The Fourier transform of this is marked by an incision in the spectrum, which is just related to this phase slip kind of signature to this local reduction here of the amplitude. This trend further continues as we go to the full power of the source of ultimately 1 megawatt per centimeter. Here we have a strong initial swing of the polarization of the magnetic orientation, I should say. Then we have a strong suppression just locally for one cycle of the oscillation. And then we have a certain recovery. And in the spectrum, we have now a sharp incision left to, or on the lower frequency side of the actual peak of the actual frequency location of the quasi-ferromagnetic mode, and then some lower frequency components here as well. So where does this originate from? To this end, we modeled the magnetic response in the material, and this is also again where the exact near field calculation of the antenna became so extremely important. So the dynamics of the magnetization in the structure can essentially be cast into one angle, which describes the antiferromagnetic vector relative to the crystallographic angles. So that we call phi. Now we have an anisotropy force in this material, which is just governed by the spin orbit interaction. So this is known from literature. And in this spin reorientation phase transition of 80 to 90 Kelvin, I'm just plotting here for reference a couple of these potentials as a function of this angle. So they have 4 local minima in each case, which shift with a temperature. Now we move to the modeling of the ultrafast dynamics. In this case, we have in the experiment included an additional external magnetic field, which leads to a resetting of these dynamics, since we want to do a pump probe type experiment. So that's more technical necessity. And now we start with the spins here in this particular potential minimum. The dynamics from the system Lagrangian can be cast in this form. I'll just very quickly, briefly walk you through the equation we have here, the time evolution of this spin orientation angle, and it contains on the right-hand side the anisotropy potential. That's just the curve you are seeing here. And then in this particular case, we have included the effect of the terahertz field here by a term that collects, so to say, the total integrated number of absorbed terahertz photons, if you like, and accordingly changes the potential in reaction to this excitation. And then we have an additional impulsive force, which can be imagined as an initial transfer of momentum just at the instant of excitation. And then we have just a damping of the spin dynamics. Now let's see how this modeling can be compared to the experiment. This is a plot of the potential landscape here as a function of the angle and as a function of the time in this direction. So let me now start a simulation of two spin species, one excited by a moderate terahertz field, that would be the blue one, and then one excited by a very strong terahertz field exceeding, or in this case, matching 10 megavolts per centimeter, that will be the red curve. So we start, there's the excitation here at time zero, both spins start to oscillate with very large amplitudes, but the blue one remains within its starting potential minimum. It performs coherent oscillations here, whereas the other one has enough initial momentum to cross the local potential barrier. In doing so, accumulating a certain phase, which is obvious here at this red marker here. So there's an opposite phase with respect to the spin that did not switch. And then as it continues to make large amplitude oscillations, going very far out in the local potential minimum and leaving the quadratic part, it accumulates more phase and eventually is in phase with the other spin again. So if we just calculate the Faraday rotation that comes from these two spins and superimpose it, we obtain a time domain signal of the transient magnetization that, at least qualitatively, already looks like what we had in the experiment. We had this initial swing, we have this phase slip signature, and then the coherent feature. And accordingly, in the spectrum, we also get an equivalent signature. But this is now where the near field calculation of the antenna came in very handy again, because now the next calculation that we performed took into account actually the near field calculated on a very small scale, on a 100 nanometer scale, with very high precision, and enabling us to calculate those spin dynamics as I just showed you for just one a single spin for the entire near field volume, for the entire structure, in fact. So that's a total of about 1 million independent cells in which we considered the spin dynamics, each locally with its own antenna near field. And then summing up all of these spins and the Faraday rotation that they cause, we could compare the calculation to the experiment. I'm showing you here for reference up here, again, the two experimental Faraday rotation transients for low field case and for the high field case. And as the next thing, I'm going to superimpose the theory, and with the near field calculation, we were just spot on and could reproduce and trace back this phase step signature to actually spins crossing this local potential barrier in a particular volume of the near field where we had these large near field amplitudes. So summing up, in this case, the antenna enabled us to drive spin switching in an antiferromagnetic material on a very short time scale, actually within about one oscillation cycle or less than the oscillation cycle of the spin itself. This spin switching is characterized by this beating feature in the time domain, a strong stretching of the first oscillation cycle because you explore these non-quadratic parts of the potential, and then in the spectrum, a splitting of the Magnum resonance. The dissipated energy in this process is a record low 1 zeptojoule, corresponding to just 1 terahertz photon, whereas near-infrared schemes usually operate at approximately 3 orders of magnitude more energy. Furthermore, this antenna already has a certain spatial definition of about 3 microns. That's a gap width of 3.5 microns to be precise. But of course, that's not the end of the line. It's well conceivable, here's the corresponding calculation, to reduce the gap size of the antenna to, for example, 10 nanometers, and thus at the same time increase the definition spatially of where you actually switch spins, and at the same time lower the necessary terahertz intensity, because here we have near field enhancement factors of, this is a factor of 10 to the 3, so 20,000 rather than 20, which could bring this scheme into reach for even oscillator-based or even chip-based terahertz sources. With this, let me move on to the second topic, which is the dynamics of Zener tunneling, interband Zener tunneling in a semiconductor driven in the near fields of a terahertz resonator structure. So this is already showing these terahertz resonators. This is actually a near-infrared or an optical image of those resonators under illumination with the terahertz field, and how these come about, I will explain in a second. So the idea is here to apply a very strong field to a semiconductor. If that field is on the order of a megawatt per centimeter, that's 0.1 volts per nanometer, it certainly is enough to drive ionization of shallow donor states, for example, in the material. That's been investigated by various groups who perform strong field experiments, Hickman's group, Cook's group, Zhang, Hebling, Keith Nelson's group, and many more. The idea here was to increase the field amplitude using metamaterial to at least 10-fold. 1.2 volts per nanometer, for example, would align the valence band of gallium arsenide with the conduction band over as little as just 2 unit cells. So that should drive strong tunneling currents in the material on a very small spatial scale. Such near field enhancement has, in other cases, also been exploited, for example, for driving phase transitions in vanadium dioxide, where also the fields could reach amplitudes and strengths sufficient to even destroy the material by dielectric breakdown. Other approaches or other experiments in this direction include metallic nanoslits, for example, the one by Daisy Kim's group, which can reach just tiny fractions of the vacuum wavelength and thus have extreme field enhancement. Also experiments from the Jepsen group with plate waveguides going in a similar direction, or for example, the control of a terahertz field at nanotips and driving emission of electrons out of these nanotips, or using an STM in combination with the terahertz field to drive tunneling from that tip into select orbitals of select molecules, just 1 electron at a time in femtosecond time windows, as performed in Tyler Cockos and Robert Huber's group. Now, in this case here, we have the semiconductor that we bias. This is a near field calculation here, again, of our resonator structure, and this is the terahertz transient that we send onto it. The calculation estimates at least 12 megavolts per centimeter on the structure. This is now a microscope image taken just with a silicon CCD of an entire array of these resonators exposed to terahertz radiation. And interestingly, they light up in the near infrared range, so you can actually see the gaps of these resonators shine brightly. This is a close-up. This is from the same microscope image in false colors, obviously, and with the resonator shape here indicated for clarity. So it's obvious that this radiation emerges just from the gaps where the field enhancement is strongest, and the calculation is just clearly congruent with this photoluminescence picture. Spectral resolution shows that we are injecting carriers well across the band gap of gallium arsenide. 1.42 electron volts would be that band gap energy, but then we inject carriers up to 1.9 electron volts, which leads to a carrier density in this case of more than 10 to the 19th per cubic centimeter. So sizable carrier density injected by the Zener tunneling process with photon energies that are just 1/500th of the highest energy photoluminescence photons that emerge then from the structure. So an extremely nonlinear upconversion process, if you like, albeit incoherent, related to this Zener tunneling, which occurs on a massive scale. Here's again just a calculation of the Zener tunneling rate. This would be without metamaterial, and then due to the exponential nature of the tunneling process, we have a 10 order of magnitude increase of the tunneling rate by this near field effect of the metamaterial. With this, yeah, well, let me just, okay, there's one more aspect I wanted to illuminate. That's the effect that this has on the terahertz transient. In this case, comparing here a low field case with 150 kilovolts per centimeter incident on the structure. That's the black curve. For reference, the curve without sample is the gray curve. And then as we go to the strong field amplitude, we see that the oscillations that we have up here, which stem from the metamaterial, from its resonance, they are almost completely gone in the spectral domain. This becomes even clearer. Here we have initially at low field amplitudes, the resonance of the metamaterial at about 0.84 terahertz or so. And then as we increase the field amplitude, the terahertz transient by this Zener tunneling ejection and carrier generation modulates its own transmission during its own just single cycle temporal duration. Okay, with this, let me go to the next field, which would be the terahertz cavity quantum electrodynamics. And here I'd also just like to quickly introduce the field, the idea of manipulating the coupling of electronic resonances to the far field actually goes back to the first half of the past century. Edward Purcell investigated how the inclusion of a resonator around an electronic excitation can modify its properties with, in fact, its spontaneous emission rate by the Purcell factor. So increasing the coupling to the far field and thus broadening the resonance of the transition. If this light-matter interaction is further enhanced, the system can form new eigenstates, which are called the cavity polaritons, which now represent a periodic exchange of energy between the two systems, between the cavity and the electronic excitation, at twice the vacuum Rabi frequency. In the terahertz range, this vacuum Rabi frequency can be made extremely large. It can, in particular, exceed the carrier frequency of light by actually up to 43%, as we demonstrated. And what this means, I would like to illustrate with this transparency, where we can inspect the light-matter coupling Hamiltonian. So we have operators that describe the light field in the cavity. That would be A and A dagger for creation and annihilation of photons. And then we have the same for the electronic excitation. So that's B dagger for creating an electronic excitation and B for the corresponding annihilation. Then, of course, light-matter interaction occurring at this vacuum Rabi frequency requires operator combinations A dagger B. That would be creation of a photon and annihilation of an electronic resonance. So that's spontaneous emission into the cavity. And then the opposite process, absorption here. But when light-matter coupling becomes extremely strong, when this vacuum Rabi frequency becomes on the order of the frequency of light, additional terms need to be considered, so-called anti-resonant interaction terms, as the ones shown here, and they contain two annihilation events at the same time or two creation events at the same time, in seeming violation of energy conservation, but in fact representing vacuum fluctuations as they occur everywhere in space, of course, as shown here with this depiction of virtual electron-positron paths being created and annihilating each other again. And if this process just happens to occur near the event horizon of a black hole, one of the two particles can drop in a very illustrative picture. And the other particle then has no partner to recombine, so it escapes into the vacuum towards infinity. And this process has been, of course, described by Stephen Hawking as the famous Unruh-Hawking radiation that leads eventually to the evaporation of black holes. So black holes, before thought to be forever stable, have actually a limited lifespan, which comes from vacuum fluctuations that lead to their evaporation. Now I'm proposing that we can create a similar situation, an analogous one, using one of these extremely light matter coupled structures, because they contain these vacuum fluctuations as well. We have these vacuum fluctuations in the ground state that correspond to certain virtual photon populations. What we would need next is an event horizon, as the black hole has. And as theoretical predictions for these cavity QED systems show, this event horizon could be implemented by rapidly switching the cavity, by switching a cavity which initially contains such a vacuum population off, disrupting light matter coupling and releasing the vacuum photon population. And in the next remaining minutes, I'd like to walk you through our progress towards this ultimate goal. First, we apply our methods of resonator design to describe ultra-strong coupling in these structures. Here we employ the cyclotron resonance of a two-dimensional electron gas coupled to our resonator structures here on top. We have a B field, a static one sitting on the sample to achieve Landau quantization. Then we send in the terahertz transient, which measures the linear transmission of our structure. And at the same time, we can repeat the experiment at different frequencies of the cyclotron resonance just by tuning the B field. So here on the right-hand side, you see vertically a spectra at a constant B field. This one here is with the cyclotron resonance turned off. We see the bare resonator mode here at about 0.82 terahertz, and then we can shift the cyclotron resonance frequency into resonance with the resonator, which then leads to this anti-crossing signature and the emergence of the two polariton states, the ultra-strongly light matter coupled state. The corresponding calculation confirms just this with an error of less than 10% and confirms here the coupling strength of a 0.1, meaning the vacuum Rabi frequency divided by the carrier frequency of light is 10%. With this design approach, we went forward to optimize these structures, first increasing the number of quantum wells, yielded a more complex resonance spectrum, but again, theory did a very good job at predicting these spectra and assigning the lower and upper polariton modes, and also thereby helping us to calculate the coupling strength and the vacuum photon population. As a next step, we looked a bit more in detail into the electrodynamics of these structures at the near field level and calculated the resonator modes of the bare structure, of the bare resonator, and then investigated what happens when we introduce the cyclotron resonance, that is the electronic excitation. So this here is showing the near field profile, the envelope of the optical mode in the growth direction. And now we include the quantum well stack. The quantum well stack does not just receive the electric field of the resonator, but rather it modifies it if it's sufficiently strongly doped, characterized by a strong dielectric function. So in fact, even a placement of the quantum well stack far away from the resonator already modifies the optical mode of the resonator quite strongly. And we observed in the design process that we could actually use the quantum well stack, the electronic excitation itself, as an additional part of the cavity. We could change the doping and change the placement relative to the resonator and achieve an additional confinement of the photonic mode by sort of squeezing the mode between the electronic system and the resonator. And this gave highlighted a path to ultimate optimization of these structures, delicately balancing the placement as well as the doping of these structures, and helped us to create these most strongly coupled structures to date yet in the terahertz range, which actually go into the so-called deep strong coupling regime, as I mentioned before, where the Rabi frequency exceeds even the carrier frequency of light. So this is a design approach as shown here. The resonator structure has a mode centered at around 0.48 terahertz. These are the corresponding spectra. For the first structure, the upper and lower polariton states here are apart by about 1 terahertz, which corresponds to a coupling strength of unity. And then as we move on and optimize the structure further, we achieved a coupling strength of 1.43. Meaning, in particular, when you interpret this vacuum Rabi frequency, that here we have almost 3 absorption events of a photon inside the cavity per optical cycle. So a single photon in the resonator doesn't even have time, so to say, to perform a single oscillation cycle of light before it is being absorbed by the electronic excitation, and then even vice versa, performing just a single oscillation cycle of the electronic polarization before it's being emitted back into the resonator. And it's these conditions that lead to this very strong population of the resonator, in this case of 0.37 vacuum photons. Now we have the vacuum photons in our resonator structure. The next task is now to implement the analogous situation of the event horizon. So that's the last topic for today, subcycle switching of these structures, which from the resonator perspective means we now create switchable, reconfigurable resonator structures that can change their optical modes and their near field distribution on very short timescales. The idea here is to incorporate into the central part of the resonator structure a switching patch that's shown here in the shape of this white patch here. It's actually made from a different semiconductor than all the other structures, indium gallium arsenide, with a different band gap that will then be selectively excited by optical excitation. But before we get there, here's a calculation of the near field profile shown from the side. So here we have again this strong near field enhancement in the capacitive region of our resonator. This is where the quantum wells are placed for the light matter coupling. So this area is where the strongest contribution to deep strong coupling occurs, where the Rabi frequency is essentially set. So thus the idea to place just here below the resonator and between resonator and quantum wells, this switching patch made of indium gallium arsenide. The switching will then occur by exciting this patch with very strong femtosecond pulses that generate a strong concentration of optically excited carriers corresponding to a plasma frequency of 80 terahertz, so far beyond all the resonances that we consider, essentially rendering the switching patch quasi-metallic. Now, what a metal does is clear. It screens the electric field that's shown here. Now we have the calculation of the unswitched part up here and of the switched resonator down here. We're essentially completely collapsing the electric field in the resonator as fast as this plasma builds up. What does this do to the coupling? Well, in the experiments, we could observe just this, the collapse of the light matter coupling strength. This here is showing a structure where the lower polariton is located here, the upper polariton is located here. The coupling strength here is 0.6. And if we now activate this switching patch way before we probe the transmission with the terahertz pulse, we go to this switched situation where the polaritons have completely disappeared. Light matter coupling has collapsed. The same can be achieved for a more strongly coupled structure. Here, the coupling strength is 1.3. And again, we can go from the unswitched to the switched case by activating this indium gallium arsenide switching patch. Now, of course, it's interesting to see how fast this can actually occur. So we went on to investigate the switching dynamics on a very short time scale. To this end, we don't just send in the switching pulse way before the terahertz probe interrogates the transitions, but rather during the terahertz probe. So now we watch the transmitted terahertz electric field while we switch the structure. This is the transmitted terahertz transient without any switching. And now this is an example of switching just at time zero, indicated here by the red arrow. And you can see how this modifies the transient electric terahertz field transmitted through the structure. Or if I take the difference, the differential response here upon switching. Next, we do this systematically, not just as time zero, but actually sweeping the point in time when we switch through the entire terahertz transient. So that's essentially this diagonal here where the switching pulse moves through the terahertz transient and interrupts light matter interaction in the structure in various phases of the polarization oscillation of the polariton states. There's a formalism to calculate from such data the linear response function, which is just the time-dependent transmission as a function of the delay after switching. That is shown here on the right-hand side. This is the transmission as a function of our switching delay at the anti-crossing point. So you see here the region of the lower polariton and here the region of the upper polariton. The switching is obvious as the switching time progresses. But what is also clear is that the lower polariton does not just vanish, but rather it seems to undergo an oscillation. Investigating this more closely, this here is a line cut through this spectrum here showing the transmission as a function of time at the lower polariton resonance. And in fact, as a function of switching delay, there's an oscillation of the transmission from the unswitched state here initially to the switched state up here, which actually, by theory, we could trace back to a very fast switching of the light matter coupled state. I'll just show you the results here. This is again the experiment. This is a simulation of the switching where the switching pulse duration is only 10 femtoseconds, just for reference. So this reproduces our experimental signature. Then increasing the switching duration to 100 femtoseconds leaves this calculation nearly unchanged. So this still reproduces our switching dynamics. But then as we increase further the switching duration, for example, to 800 femtoseconds, there are deviations, clear deviations. This switching oscillation is smeared out. It's now just a almost monotonic increase of the transmission. And this way we could place an upper bound on the switching duration of 100 femtoseconds, which is the switching time in these structures. So what does this mean? We have a lower polariton frequency of 0.5 terahertz. That's a cycle duration of 2 picoseconds. And then we switch the state off in just 100 femtoseconds. So that's just 5% of the cycle duration of the lower polariton. And this is, in fact, the very non-adiabatic dynamics that would be required to unleash these vacuum photons in switching events. Switching off light matter coupling faster than the vacuum photons can dissipate adiabatically, forcing them to be released. This is not the end of the story. We have both ingredients at hand now, the extremely strongly coupled structures and the functionality to switch these resonators and also to do all the necessary calculations to calculate their properties. And the next step is now clearly to go to towards the detection of these vacuum photons. One such scheme I'd like to mention was invented by actually Christina Beniak-Hermusch at Jerome Feist's chair at the ETH Zurich, where they developed a correlation method to investigate the spectral characteristics of non-phase stabilized terahertz fields. So, for example, thermal radiation, or also for these matters here, vacuum radiation, as it would emerge here out of these structures. The idea is essentially to measure the first order correlation function. I refer you for details to these publications, but as a simple sketch, this would mean sampling the terahertz field with a fluctuating nature, not just at one point in time, which would give an average value of 0 in the field, but rather to sample the field at 2 distinct points in time and then compare these, which would lead to a net signal that could then be related to the spectral nature of this radiation. With this, let me acknowledge the work that's gone into all of these projects. As I was introduced, I'm now working at the TU Dortmund University, where I'm setting up a group just now. But the experiments that I've shown you here were all performed in the Rupert Huber's group during my time still at the University of Regensburg. Dominique Boujat was our project partner for semiconductor structuring and growth. The magnetic experiments, the spin dynamics were investigated in collaboration with Rostislav Mikhailovsky and Alexei Kimel and Anatoly Svetstin. Support for the theory on the cavity QED experiments was by Cristiano Ciuti. And of course, the numerous PhD students that have dedicated their times and effort for these projects. Thomas Mark, Sebastian Bayerl, Thomas Ebnet as a master student, Stefan Schlauderer, Darren Volovchin, whom I don't have a picture of, Christoph Schmidt, Andreas Bayer, Maike Halbhuber, Joshua Moninweg, and Matthias Knorr and Jürgen Raab. And with this, let me just go to the conclusions. I've shown you how it's possible to tailor light-matter interaction in terahertz resonators by calculating and shaping by the resonator structure the near-field structure towards certain functionalities. This was exploited, for example, to switch spins with minimal dissipations driven by the terahertz field with record low energies of just a septojoule per spin that is switched. Massive nonlinearities, on the other hand, can be driven by strong terahertz fields in corresponding metamaterials. That includes, in this case, Zener tunneling. And in the last part of the talk, I've shown you a glimpse into the world of terahertz cavity QED, where we've investigated deep strong coupling on the one hand, but then also the possibility to make switchable metamaterials to collapse a deep strong coupling on an extremely short time scale, and to finally go to investigate these vacuum fields. And with this, I've completed my journey through this field of terahertz resonators. And I'd like to thank you for your attention, and I'd be happy, of course, to take questions.
All right, well, thank you very much for that presentation, Christoph. We will open the webinar up to questions now. So if you have a question and have not yet submitted it, please go ahead and do so. You can find the Q&A button at the bottom of your Zoom window. So I'm going to turn the floor to Christina to ask our first question. Christina?
Thank you very much, Hannah, and thanks so much, Christoph, for this fascinating talk and giving us so many examples where sub-wavelength resonators can be used. I will start with a question from the audience, which goes more into, how shall we imagine the situation of having 0.37 photons per resonator? Like how can we imagine that? What does this mean, a fractional number of photons?
It's an expectation value, yeah. So this value is derived from essentially calculating the expectation value of photons for the ground state of the structure. For reference, if you take an empty resonator, the expectation value would be 0, just no photons in the resonator. In this ultra strongly coupled state, which is calculated essentially by a Bogoliubov transformation from going from the basis of just the photonic and just the electronic states into the basis of the coupled states. And in this basis of coupled states, for a sufficiently strong coupling, in that case, omega Rabi equals 1.43 times the carrier frequency of light, the expectation value for the number of photons in the resonator is in fact not 0, but 0.37. So on average, you could say, or if you had 100 resonators, you would expect 37 photons in this ensemble of resonators. I think that's maybe a more tangible example.
Yes, I think so. Okay, then I'm gonna continue with the two different questions that we received regarding the resonator design, because this, as you underlined very nicely, plays a crucial role, right, in the enhancement of the field and the physics that you can investigate, the regimes that you can reach. So,
absolutely, yes.
The first question would be, how do you choose actually the shape of your resonator and antenna? Is there an optimization process in that sense? And linked to that would be the second question, like since you study phenomena on these very short time scales, the antennas need to be ultra wideband to accommodate your broadband terahertz fields. Like, have you considered to bring designs of ultra wideband antennas to your structures beyond perhaps the bow ties that you have shown?
Very good questions. Yeah, let me start with the first one, the how to choose a terahertz antenna design to achieve a certain functionality. We had two examples. The one that enabled the spin switching, it was this open design, bow tie design. On the other hand, we had the ones for the cavity QED structures, two different designs which are more narrow band. So the wideband nature of the bow tie essentially comes from leaving out the inductive outer loop. So that's actually already an extreme example of a wideband antenna. You could make it even more patch-like. You could increase the width of these lobes perpendicular to the field orientation, thereby actually offering even more current paths that are possible. So different resonant frequencies in that one antenna, and thus changing this antenna to even more broadband response. On the other hand, when you want narrowband response, it's advisable to work towards minimizing the dipole moment of the antenna, of course. So there you can play with the gap sizes. You can try to minimize the classical dipole that the antenna represents, to minimize the coupling to the far field. One aspect I didn't talk about are antennas that try to minimize the dipole by going towards a kind of quadrupolar approach, which has been investigated first, I think, about 10 years ago by it's a PRL by Ibrahim Al-Naib. I don't have the reference on top of my head. So that would be another approach to go towards a narrowband structures. Also, there are ideas of investigating Fano-type resonances and coupling several resonances to achieve certain narrowband functionality, and also, for example, to make fractal structures where you don't just have one obvious central capacitive gap element, but maybe you have certain side circuits in the antenna that are again resonant at higher frequencies. Mm-hmm. The problem is then that you don't have one particular location where you concentrate all the fields, but different parts of the resonator structure will enhance the field depending on the frequency that you send in. For the second part of the question, thanks very much, because this gives me the opportunity again to stress that the dynamics are not necessarily connected, depending on which phenomena you investigate, to the bandwidth of the antenna. And that's true especially when you investigate non-perturbative phenomena. For example, phenomena that have an extreme nonlinearity as a function of the incident terahertz field. Let's stay, for example, with the interband Zener tunneling. If you have a very low field amplitude, generally the Zener tunneling rate will be low, but due to its extremely nonlinear nature, the rate will be strongest near the maxima of the terahertz field amplitude, and this nonlinearity will actually sharpen the time window by a great amount, even the more so the stronger the nonlinearity is, and limit the time window where this nonlinearity actually, or where the process is driven, to much less than the cycle duration of the terahertz wave. So even with a 1 terahertz carrier wave, you could imagine a nonlinear process that occurs only within a 50 femtosecond window significantly. So as soon as you have extreme nonlinearities, non-perturbative nonlinearities in particular, the timescales of the oscillation cycle of the resonator mode and the timescales of the effects that you drive can be very dissimilar.
Yeah, that's very exciting. Okay, thank you very much. I will continue with one question that we received also from the audience. Maxime says, thanks for the fantastic talk, Christoph. He'd like to know your thoughts on the possibility of, observing the dynamical Casimir effect at other frequencies. For example, in the mid-IR and above, right? You showed a lot of like terahertz experiments. What do you think would be the best strategy to pursue those?
Well, first of all, I think going for these physics is interesting by itself, and I wouldn't tie it to a certain spectral range, but there are certain advantages that the terahertz range has. When you consider, for example, the visible range, there's actually a Nature paper by Stefanie Reich's group who achieved in the visible range with plasmonic structures coupling strength of on the order of 1.8, if I remember correctly. Yet those are visible frequencies, and it will certainly be challenging to modulate light-matter coupling in the visible range on an extremely sub-cycle timescale. You already have cycle times on the order of a few femtoseconds. You would have to go to attosecond modulation times, which certainly is possible somehow, but very much more challenging than the situation we have here, where we have picosecond oscillation cycles, still very strong coupling strengths, and the possibility to manipulate these systems on few femtosecond timescales. So I think when you want to go to vacuum fluctuations in the optical regime, I would consider terahertz optical because it's free space coupled, certainly. Then the terahertz range does have these advantages.
So the terahertz is somehow a sweet spot for this. Okay, Christoph, thanks so much. I will close maybe with one question from my side. Namely, you have shown so nicely this spin switching, right? But so far you still need quite high fields. Do you think it will be at some point within the reach to switch one single spin by one single terahertz photons? And how far away are we from that? Yeah.
Probably quite a bit, somewhere in the middle. Let me put it this way. So there are different aspects here to unfold. I showed you this additional antenna design at the end, where we just have this 10 nanometer gap and field enhancements of 20,000 rather than 20. So a factor of 1,000 in the field means a factor of 1 million in the intensity. So this is drastically lowering the intensity that is needed from the side of the terahertz source. On the other hand, when you go to smaller and smaller structures, when you go to smaller and smaller domains, certain aspects of this magnetism in general will have to be considered. For example, there's obviously a limit to the stability of a magnetic domain as you shrink it more and more. So thermal fluctuations will start to attack your magnetic states as you decrease the domain size. Decreasing these domains to a single spin is, with this argument, essentially out of the question. The question is even, what is even a single spin in this material if you go to just, a fractional unit cell, which doesn't even make sense. So the nature of this particular magnetism, this antiferromagnetism in this material, would not even exist anymore. So you need a certain minimum size of your domain. And I would say this domain size is ultimately given by the size that is still robust against thermal fluctuations. I guess that would be a limit, but that's small. That's a few nanometers.
Okay, thank you so much, Christoph, for this amazing talk. And in the interest of time, I think I need to close this webinar here. But it was very exciting to listen to you and learn about all this physics. So yeah, with that, I give it back to Hannah. And thanks so much, and have a nice evening, afternoon, everyone.
Thank you so much.
All right, well, thank you both. And thank you all for joining us for today's webinar. As a quick reminder, you will receive a link to the recording within 48 hours by email. And then when you disconnect today, you'll be prompted to complete that short survey and provide us with your feedback. So once again, thank you, Christoph, for being here. And thank you to Christina and Dimitrios and our Photonic Materials technical group for organizing this webinar for all of us. We hope to see you next time. Bye, everyone.
Thanks for having me. Goodbye.